that all good?
That's good.
Perfect. Are we recording? You said? Okay, perfect. Okay. Yes, good afternoon, everyone. I'm Cam, and I'm a first-year PhD student here at the University of Oxford studying chemistry. And my research is centered around developing new sustainable plastics, particularly elastomers and rigid engineering plastics that are from bio-based materials and able to degrade at the end of life. And that's why I wanted to talk to you guys today about the future of plastic, the environmental challenges that we currently face, and some of the solutions that we can undertake to try and remedy these problems that we're now facing. But before I get into that, I just wanted to give you a bit of background about me. I went to my local comprehensive school in Enfield in North London, Highlands. I did my GCSEs there, and I stayed on to do my A-levels, where I did chemistry, physics, maths, and further maths. I then decided to stay in London for my undergraduate degree. I did a integrated master's in chemistry at University College London, or UCL, which is an amazing university, and I had an incredible time there. So if you're looking at universities, I highly recommend looking at UCL as well as Oxford. And it was during this time that I was first exposed to chemical research. I was lucky enough to be awarded some funding to work with Professor Robert Palgrave doing some solid state chemistry. And then in my fourth and final year, my research project was with Dr. Claire Bakewell, looking at switchable catalysts to make sustainable polymers. And this was my first interaction with catalysis for sustainable polymers and making materials. And I really wanted to continue it going after finishing my undergraduate degree. So I applied to Oxford to do my PhD, and I was lucky enough to get into Trinity College, where I'm now studying for a DPhil. This is just what Oxford call a PhD in inorganic chemistry for future manufacturing. I'm in the Williams group, which I'll come to talk a bit more later. But before I do, the other thing I want to quickly address is, what does a chemist do? Because I think there's a lot of misconceptions around this, and I think particularly in my own family and friends circles that people don't really have an understanding of what I do, and I don't think I knew what a research chemist did when I was studying A-level chemistry. The most common misconception is people think that I'm trained to be a pharmacist and fulfill prescriptions, and this is incredibly important work, but not what I'm training to do. The other thing is what my parents, I'm sure, can constantly think I'm spending time in the lab doing, just setting fire to things and blowing stuff up. Again, not what I'm doing. And the most common thing I get from my friends who aren't chemists are, oh, could you do what Walter White does in Breaking Bad? And again, no, I can't. None of these are representative of what I do on a day-to-day basis. So what do I actually do? Well, I'm lucky enough to work in a very big team of very talented chemists from all over the world. We're a very diverse, multidisciplinary team. You can see this picture from the Williams group in 2019. Unfortunately, because of COVID, we've not been able to take a more recent one. And we call the Williams group because our supervisor and person who leads our group is Professor Charlotte Williams, who's a fantastic, really inspirational chemist. And all of our research focuses on the study of metal complexes for their use as catalysts to make polymers, fuels, and new materials. So essentially, we're all trying to plug away at this big question: how can we produce new sustainable plastics and polymers to replace the petroleum non-sustainable ones that are so common in all of our lives at the moment? I want to go into a little bit of basics about polymer chemistry. I'm sure some of you have covered this in GCSE or in your A-levels, but I just wanted to go over it for anyone who may not have come across this. So what are plastics? Well, they're made of long chain molecules called polymers, and this is where polymer comes from the Greek poly meaning many and meros meaning parts. And these are long chains of molecules made up of much smaller molecules we call monomers. And by enchaining these smaller molecules together, if you think like linking paper clips together, we drastically change their properties, and we have these very big macromolecules that have lots of very interesting properties. But like with all kinds of chemistry, nature beat us to mastering this first, because we often think of plastics and polymers as very synthetic materials, but there are plenty of examples of polymers in nature. DNA and proteins are essentially just polymers made of amino acids, and cellulose is a material seen all over the natural world. These are really interesting and important materials, but not the focus of what I'll be talking about today. My talk's going to focus around this kind of plastics that probably come to mind when you hear the word plastic. So one very common application for these materials is packaging. It's hard to find any item in the supermarket these days that doesn't come in a form of plastic packaging. And this is because plastics are relatively cheap, they're lightweight, they can be any color or shape that we want. They can be hard, they can be soft, they can be stretchy or hard. They're ideal materials for this. And they're also chemically inert, which means whatever we put in the packaging isn't going to react with the container, which is obviously very important. But these kinds of plastics are just the tip of the iceberg in terms of applications. Your smartphone, your computer, the device that you're watching this talk on right now is packed full of different plastics, whether that's the casing or the keyboard or some very advanced electronically conductive polymers in the circuitry. And there's also loads of polymers in your clothes. I'm sure everyone watching this talk at the moment has some kind of polyester or nylon in an item of clothes that they're wearing. And the final real advantage of polymers is that they're amazing for a range of different medical applications. And we've seen this in abundance over the last 16 months of the COVID-19 pandemic, that we need lots of PPE. And plastics are ideal materials for this. They can be transparent, they are clean, they can easily wipe them down, they're cheap and lightweight. And they can also be used to make loads of syringes, ideal for administering life-saving COVID-19 vaccines. So plastics are everywhere. The 21st century, our 21st century society is built on the fact that we have loads of plastics for a range of applications. But the word plastic has also become quite an evocative word with lots of negative connotations. So I'd love you guys to head over to the Slido where you answered some questions from Richard and Chris, Trinity Talks 9, or you could just scan this QR code. I just want to hear what you think of plastics. Just one or two words. What's the first thing that comes into your mind? Almost like word association game. You know, when you hear that word plastic, what are your first few thoughts? And I'm going to give you some time to do this. I'll leave this QR code up for the next couple slides while I talk about something else, and we'll come back to this in a short moment's time. So how do we make polymers? Well, there are two traditional ways of making a polymer in industry. These are the most common. So there's addition polymerization, where we have our monomer, shown by this red ball, and we add a catalyst, and we can enchain these monomers together. And typically monomers here look like this compound here, ethene or ethylene. We can catalyze that, we can open up this double bond and form a long chain of carbon atoms, each bonded to two hydrogen atoms. And this is polyethylene or polyethene, and this is typically what plastic bags are made from. The key here is that all of the atoms in our monomer are now being converted into our polymer. And I also just wanted to show you guys this kind of notation. Maybe you're probably not so familiar with it from your GCSE and A-level, but this is the skeletal notation, and as chemists we're really lazy. We don't like to draw out all the carbon and hydrogen atoms every time we draw a molecule. So we just say each point of the line is a carbon atom, and depending on the bonding, we assume there's the right number of hydrogen atoms. So here's ethene, and here is polyethene, where N is just a big number as well, I should have said. And this is our repeat unit, so we have long chains of these molecules repeated over and over again. The second most common type of polymerization is condensation polymerization, and the difference here is that we have two different monomers. Traditionally a dicarboxylic acid and a dialcohol. And this carboxylic acid group and this alcohol group can react together and condense to form this ester linkage. And in the process, and unlike additional polymerization, we're kicking out some of our atoms in the form of a small molecule, and in this case water. And because we've got this difunctionality, we can grow our polymer chain from both sides, so we can get lots of repeat units all lined up together. And again, I just wanted to show this skeletal notation where we've got our dicarboxylic acid, our dialcohol, and our polyester. Okay, so I hope you've all had time to head over to Trinity Talks 9 and to Slido. I'm going to try and attempt to share this now, and we'll have a quick chat about your suggestions. Okay, oh, I can see lots here already. Cool. Useful, microplastics, pollution, ocean pollution harms turtles, yes, water pollution. Harmful to animals, plastic is great, bad for the environment, harmful, dangerous, animal killer, won't biodegrade. Yeah, these are fantastic. There's a great range of different thoughts on here. Recyclable, environmentally damaging, Yeah, so you guys are, even though I've not really touched on this yet, you guys are more than aware that these plastics can be really harmful. We've got microplastics there, straws, exactly. I love plastic, me too. Permanent, depend on them too much. These are fantastic suggestions. Litter, recyclable. Yeah, so like I was saying, the term plastic is incredibly divisive. I think these days it's pulled on a lot of meaning that maybe it didn't 10, 20 years ago. Okay, let me try and share my slides again. Okay, yeah, so you guys touched on pretty much all the key themes there surrounding plastic and what I'm going to be talking about today. And there's the question of why is there so much plastic? Why is there so much ending up in the ocean and wasted in landfills? Because at the moment, well, in 2018, humans produced 359 million tons of plastic. And as of 2015, humans had produced a total of 8,300 million tons of plastic. And of that, 6,900 million tons is already waste. So that's nearly 7,000 million tons of plastic in landfills in our ocean, and only 9% of that was ever recycled. And the problem here is that you might be thinking, well, we've got paper straws now, we have to pay 10p to use a plastic carrier bag, we're cutting down on amount of single-use plastic in the UK, and this is true, but this doesn't match the global trend. We're seeing a lot of developing countries having a growing demand for plastic, and this is driving up global demand with some of the world's biggest petroleum to virgin polymer, so polymers that haven't been recycled, essentially fresh from the oil. Some of these companies are building the biggest plastic producing plants the world's ever seen, which might be a bit of a shock. It was to me, because I thought the trend was that we're cutting back on plastic, but that's just not the case. And this is because cheaper, virgin polymers and producing polymers straight from petroleum is much, much cheaper than recycling plastic. At the moment, it costs too much to separate plastic, to melt it down and produce a useful material afterwards. So there's just no incentive for industry to get behind it. And I highly recommend checking out this article by David Shukman from the BBC about how just 20 companies are producing more than half of the world's single-use plastic. And like was touched on in the word cloud, a lot of you identified that plastic pollution is a huge problem. But the other environmental factor we have to consider is producing plastic releases huge amounts of CO2. In 2019, the plastic industry produced the equivalent of 200 coal-fired power plants of CO2. That's enormous quantities of carbon dioxide being pumped into our atmosphere. And as you can imagine, actually, you're all well aware, I'm sure, that carbon dioxide is a greenhouse gas. It's contributing to anthropogenic climate change and resulting in the more extreme weather we're seeing all over the world at the moment. So there's a number of problems surrounding plastic as a material. And like you identified, plastic can kill sea turtles. It's very bad for all living organisms in the ocean. Fish and mammals can get caught in these larger pieces of plastic and get hurt or potentially die from them. And like rocks or pebbles on a beach, these plastics can erode and break down into much smaller pieces of plastic, either micro or nano size, called micro nanoplastics. And these are quite scary materials because, to be honest, we just don't understand how they behave in living organisms. They're bioaccumulating in lots of different animals, in fish, with fish on either side of the Pacific Ocean. At food markets being found to have microplastics in them. There's been microplastics found in drinking water in Western Europe. And we just don't know the long-term health effects of these materials accumulating in animals and in our own bodies. And we were doing quite well, in the UK, particularly for cutting back on plastic, but the COVID-19 pandemic has set this back a little bit with this article from the Times talking about how there's currently 100 million discarded face masks every week at the moment. It's a huge amount of waste, a huge amount of plastic that's only going to end up in landfill. So it can all be quite depressing and overwhelming, and I realise that. So I want to spend the rest of the talk discussing some of the potential solutions we have going forward of how we can address a lot of these issues. The first solution might be quite obvious, is that we need new sustainable plastics. The plastics derived from petroleum are not going to suffice as we go forward, and our dependence on plastic materials isn't going to drop. So we need to replace these with much greener alternatives. And I put this picture up here and I call it the Holy Grail because I really like it. This is what we're aiming for, a closed circular economy of plastic. So this is where we can have raw materials that we can produce monomers from. So these could be plants, they could be waste from different industries, and I'll come on to that a bit later. But we want to take those renewable resources, extract our monomer, make new polymers out of them that can have a range of different applications to replace all the types of plastic that we use at the moment. And then we want them to be recyclable or reprocessable at the end of the product's natural lifetime. And then if it can't be recycled, or if it's been recycled too many times and has to be thrown away, then it could biodegrade in the environment and break down into environmentally benign products. So we need to find new methods to turn renewable resources into monomers. That's one of the key challenges. And the other is that making plastics that are easy to recycle isn't easy, especially if we go to more complex polymer architectures. And when designing polymers, we need to consider the sustainability of the material over its entire lifetime, and that isn't easy. It's called life cycle analysis, but we need to get much better at doing this to assess, okay, how does this polymer behave before, as raw materials, when it's being produced, when it's being used, when it's being thrown away? What are each of those stages? What effect does each of those stages have on the environment? And finally, we need to further understand the relationship between the structure of the polymer, so as we draw out our chemical structures, how that relates to the properties, so that we can better design materials from our new sustainable monomers that can fulfill particular applications. The second solution is we need to get much better at recycling. As we saw, only 9% of waste plastic at the moment is recycled. And there are a few different recycling cycles you can consider, and they're up here. So the first one here is just if we have renewable resources, that's obviously sustainable. If we grow a plant and harvest that for monomer, we could regrow that and have, in theory, an infinite supply. If we have a product and it's not damaged by the end of the product's lifetime, we could just reuse that. That's a form of recycling. The one that probably comes to mind to most of you when you hear the term recycling is mechanical recycling. This is where we have our plastic water bottles, we break those down, we melt them down, and then we recast new plastic water bottles from that melted plastic. And this is how a lot of recycling occurs at the moment. But the problem here is that each time we melt down our plastic, we start to degrade the mechanical properties of that material, and they get weaker and more brittle and less reliable as a product, essentially. So this is why chemical recycling is becoming a hot area of research at the moment. And this is essentially where we have our chain, our polymer, and we can depolymerize it. So we take the polymer and turn it back into its monomers. And then from that batch of monomer, we can repolymerize it to form a fresh polymer that will have in theory, the exact same properties as the polymer that we depolymerized. And there's a lot of research in this area at the moment, and I think it's probably our most viable bet to opening up recycling, because we could separate the monomers quite easily from a range of different plastics and then produce new materials. And then finally, energy recovery and carbon utilization. So this is almost like a last resort where we would essentially incinerate our polymer, our plastic waste, harvest the energy from that to produce electricity, and then use carbon capture technology to stop any carbon dioxide escaping into the atmosphere. And we could even potentially use that carbon dioxide as a monomer, which I'll come to talk about near the end of my talk. But to do this, we need new technologies that make the widespread recycling of plastic much easier, cheaper, and greener. And this will require the development of new catalysts capable of turning polymers back into their constituent monomers, which we're working on now, and we have some, but they're just not essentially good enough to deal with real-world plastic waste yet. And the final solution is we need to better understand the degradation of plastic. We need to understand the routes and the mechanistic pathways that plastics take when they degrade. And we need to find ways to reduce the cost and improve the performance of existing biodegradable polymers. There's quite a few on the market already, like polylactic acid that you might have heard of. But we still currently don't understand how they behave when they degrade in the environment, and obviously this needs to be better understood as we move forward. But the key problem with understanding degradation of plastic is that plastics have very different structural features at different length scales. So, for example, we have the chains, but then as we go to we sort of zoom out, we get much more crystalline regions within a plastic, and this gives it rigidity and strength. But these areas of crystallinity are in amorphous areas, so much softer regions. And as you can imagine, the softer regions can be degraded much quicker than the harder regions. And so this makes a very complex picture that we still need to get our head around. And finally, we need to produce polymers that degrade on demand. So we want to produce, for example, I keep using the example of a plastic water bottle, but we want a plastic water bottle that won't degrade while it's being used, because obviously if we add water to it and it starts to fall apart and degrade, it's pretty redundant as a product. But if we could take that plastic water when it's being done and trigger degradation under some mild conditions, then that would be perfect. So now I want to come to talk about what we do in the Williams group at the University of Oxford. And in particular, I want to talk about this area of materials called Thermoplastic Elastomers, which have a wide range of applications, from the soles of your trainers to rubber bands to electrical cable insulation to pressure-sensitive adhesives, so the sticky part of sticky tape or sticky notes. And these polymers are typically composed of what we call ABA block copolymers. And this is where we have two different kinds of polymers chained together. So our A blocks are much harder and rigid, and our B blocks are much softer. And the B block is sandwiched between two lots of A. And these give the hard regions here, so the A blocks, can physically cross-link with each other. And this, in combination with the flexible and extendable nature of the soft region, means we can have a material that exhibits high ultimate tensile strength and strain at break. And another cool phenomenon we often see with these materials is they do what we call phase separate, where if you could think of it like oil and water, like likes to be with like, polymer A likes to be with polymer A, and polymer B likes to be with polymer B. So in the solid state, they can adopt these interesting morphologies where we have either spheres, cylinders, gyroids, lamella, and these different morphologies have produce different properties for our material, and therefore we can tune the morphology that's adopted by changing the size of the blocks, the length of the chain, the type of polymer that the blocks are comprised of, to tune the morphology we adopt and therefore help us tune the properties and the applications that polymer would be good for. Another area that we're really interested in is using sustainable monomers, like I've mentioned. So we can use CO2, we could use terpenes, so these are compounds derived from plants. In particular, a particularly exciting one of these is limonene oxide. So this is a compound that comes from citrus peels, so oranges and lemons. So if you think about the orange juice industry that produces huge quantities of waste orange peel every day, could we take that waste, extract limonene, produce limonene oxide, and then make a useful polymer from that and a useful material? So literally turning a waste into something that's useful and has value. We can use vegetable oils, so unsaturated fatty esters. Carbohydrates can give us a whole range of different monomers. The key of these is probably lactide to produce polylactic acid, which is, like I mentioned, a very common biodegradable plastic on the market today. But of all of these, the one that we're probably most interested in our research group is CO2, because CO2 is also a waste product. We want to remove it from the atmosphere. It's very cheap. It's contributing to climate change. So can we use this to take it out of the atmosphere, make something useful out of it, and eventually give it real value? So we're interested in copolymerizing CO2 with epoxides to produce polycarbonates. And these materials can be used for a wide range of applications. At low molecular weight, so when our chains are very short, we can have elastomers, foams, coatings, and adhesives. We move to much higher molecular weight, so longer chains, we can produce rigid plastics and even better elastomers. So I want to come on to a piece of work that was published last year by our group, mainly carried out by my amazing mentor, Greg Sully. who developed this catalyst. And I wanted to show you what this catalyst looked like. It's quite a complicated molecule, but I always think in GCSE and A-level you hear the term catalysis and that it lowers the activation energy without being used up in the reaction. But you don't really see or think about what catalysts look like. Well, that definitely was the case when I was doing my GCSEs and A-levels. So here we've got a dinuclear, heterogeneous dinuclear catalyst, meaning that we have two different metals here, zinc and magnesium, coordinated into this big macrocyclic ligand. And then each metal is bonded to a C6F5 ligand. So this is called a organometallic bond. And we can combine this catalyst with an initiator, and shown here is cyclohexene diol. And then we can initiate a polymerization. And in this work, they polymerized decalactone, which again is a very exciting monomer because this can be derived from castor oil, which can come from castor beans, which again is another renewable resource. And we can catalyze this to produce a mid-block of soft polydecalactone. And the really cool part is we can introduce CO2 into our reaction mixture, which can insert into this metal bond and then go on to react with a molecule of epoxide in what we call ring opening copolymerization to produce our hard blocks at either end. And because we switched from ring opening polymerization to ring opening copolymerization, we call this switch catalysis because we switch between two different distinct mechanisms, which is a very cool phenomenon. So what does this molecule look like? What does this polymer look like? This is it drawn out in the skeletal form. So we have this big soft block in the middle of decalactone with our initiating species sat right in the middle. And then we have our polycarbonate at either end. And like with all compounds, chemists are really bad at naming things and giving things catchy names. So this has the name polycyclohexene carbonate, block epsilon decalactone, block cyclohexene carbonate. Really rolls off the tongue. But this is a really cool material. I think so at least, because we can tune its properties by controlling how much CO2 we put into the polymer. So at just 6 weight % of CO2, we can produce a very soft and sticky polymer that's a really good pressure-sensitive adhesive, and actually better than a lot of the tapes and adhesives that are on the market today. So you can see it's stuck here onto a bit of plastic, a more flexible plastic backing. We can go up to 9% and have a much more elastic polymer. These materials are great elastomers. And then we can go up to 16% of CO2 and have a much harder, much more rigid plastic. Probably ones that you're most familiar with or think about when you think of plastic. So this is great because just by tuning the amount of CO2 we put into our polymer and where we put it, we can change its properties and therefore its applications. And the final great advantage of this polymer is that it's packed full of carbonate and ester linkages. So these are bonds, sort of functional groups here, where we've got two oxygen atoms with a bridging carbonyl in the middle, and then esters are similar, but we have an extra carbon atom here instead of oxygen. And unlike we get in most petroleum-derived polymers that just have carbon bonds in the backbone, these carbon-oxygen bonds allow the material to be susceptible to hydrolysis. So if the material's in water, maybe with a slight bit of acid or base, these bonds can be broken. And so this gives us loads of different points along the polymer chain that we can essentially break up our polymer and degrade it. And so these highly oxygenated polymer backbones are really advantageous in terms of degradation. So I wanted to come back to this picture I showed earlier about the Holy Grail and just sort of go over how the Williams group, my research group, are trying to address each of these points. So like you saw, we're trying to use renewable raw materials, decalactone from castor beans, or CO2, or limonene oxide from orange peel, and we're trying to make a whole range of different polymers from those that have wide-ranging applications. And like you see, we're looking at ways that we can tune those properties and those applications. And then we want those polymers to biodegrade and break down in nature at the end of their natural lifetime. And then the other area that we're starting to look at more and more now, and I hope to look at more as my PhD progresses, is how good are these materials at being recycled and being reprocessed? Do they hold their, do they keep their mechanical properties after being melted down and reformed over and over again? I think this would be a very important area to move forward and produce greener polymers. So I'm just going to conclude my talk now by saying, just going over some of the key points, so that polymers are molecules made of long chains of smaller molecules called monomers. They're traditionally made through addition or condensation polymerization, but like we've seen, there's a lot of other ways we can make polymers, and particularly other ways to make sustainable polymers. Plastics are these wonder materials that have extremely desirable properties, but it's those properties that have made them so useful that is resulting in them persisting in the environment for incredibly long periods of time. So we need new sustainable polymers comprised of renewable monomers and which are able to degrade in nature on a reasonable timescale. We need to improve how we recycle plastics. We need to better understand polymer degradation. And I hope I've shown you that in the Williams Group, we're working hard to try and address some of these problems to enable a greener future for plastic. Because eras of human history have always been defined by the materials we've used. So we've had the Stone Age and the Iron Age, and it's often said that we're now in the Plastic Age. And while the time to prevent the damage plastic pollution can cause is probably past, the time to change the future of plastics is happening now. And I hope to be a part of that. And I hope a lot of the future scientists in this call will also help solve these problems. So I wanted to quickly give some sort of supracurricular enrichment recommendations, following on from what Rich and Chris said. Some books that I really like that are related to my area of research are Stuff Matters by Mark Miodownik, which I actually wrote about in my personal statement when applying for university. This book that came out this year by Anna Pajajski called Handmade. If you're interested in material science, it's fantastic. I highly recommend it. If you're interested in the sciences, in particular chemistry, or just life in general, I guess, I highly recommend Primo Levi's The Periodic Table. It's about life of Primo Levi, a chemist working in northern Italy during the rule of Mussolini, and his time at Auschwitz, which is an incredibly moving story. Some podcasts, I'm sure you've all heard of The Infinite Monkey Cage, and Scisode Tangents is a sort of American version of that, hosted by Hank Green. The Life Scientific, hosted by Jamal Khalili, where he interviews a different field-leading scientist every week and about what brought them to their point in the career they're at now, which I always find fascinating. Radio Lab's a fantastic podcast looking at lots of stories from the full range of the scientific spectrum. And then finally, if you're particularly interested in what I've spoken about today and plastics and how we solve some of these problems going forward, I highly recommend going to the Royal Society of Chemistry's website and reading this report. It's free to download as a PDF. It was published last year. It's called Science to Enable Sustainable Plastics, and it goes into far more detail and depth than I could possibly do in this time today. So all that's left for me to do is say thank you to Trinity College, Oxford, and particularly Richard and Chris for letting me speak to you guys today, my PhD supervisors, Professor Charlotte Williams and Professor Clive Sivior, for their mentorship, the whole of the Williams Group, but particularly Greg for his help in the start of my PhD, the Oxford Inorganic Chemistry for Future Manufacturing Centre of Doctoral Training and its industry and instrument partners for funding my research. If you'd like to get in contact with me about anything I've spoken about today, please feel free to email me at cam.poon@trinity.ox.ac.uk. You can follow me on Twitter, where I try to post a lot of the cool things I'm doing in the lab. And finally, thank you for listening, and I'm happy to take any questions about anything I said today or about university life and PhD life in general. Thank you.
Wow, thank you so much, Cam. That's absolutely lovely, and I loved, as I said last week, I love that selection of enrichment resources you gave us at the end as well, which rather neatly dovetailed between the two sections of the talk. But what inspiring and passionately delivered area of work you're involved in.
Oh, thank you.
Some questions have emerged on Slido, yeah. So if I may put those to you. On a minor note, great question just was, would it be possible to post the PowerPoint? Yeah, that goes out with the follow-up email tomorrow. There'll be a PDF of this presentation, so definitely send that across to you all and all those registered. So let's go into the questions relating to the content. A specific one: what's the maximum amount of CO2 you can add to a polymer or to the polymer?
Great question. So we can make what we call the homopolymer of this, so where we just have this polycarbonate, and that would have an enormous amount of CO2 and much more than we're getting up to here. The problem with what we is that material would be called polycyclohexene carbonate, and it's actually quite a good material in some sense. It's mass produced on a relatively large scale, but it's very brittle. And this is a problem with a lot of the sustainable polymers that are produced, that just the homopolymer, so just one chain of one kind of polymer, typically doesn't have amazing mechanical properties, and definitely not the kind of properties that can rival the petroleum-derived polymers. So this is the advantage of the switch catalysis and producing these block copolymers, where we can combine a much softer polymer with a much harder, brittle polymer to be able to finely tune the properties that we can achieve. So yeah, in theory, we want to get as much in as possible, but there's a limit. I'd have to sit down and work it out what that would be. But yeah, we could get much, much higher, but at the expense of the material's properties.
Great. And then on a related note, does the use of CO2 in these plastics offset the amount that might be used in their products or transport or use or disposal? In other words, does the lower amount of CO2, I suppose, make them more carbon neutral?
Well, yes, definitely. If they're fully carbon neutral, it depends on. We produce these materials on a relatively small scale on a research lab. If they depend, obviously, on how industry would scale them up and the procedures they'd do that. You'd hope that it would be as green as possible. But yes, by using CO2 as a resource, you're massively offsetting the amount of carbon dioxide that you're producing. And it's not only is it making useful material, but you're also finding a way to just trap the CO2. Producing these kind of polymers isn't the solution to all of that, but if we have more and more technologies and materials where we can absorb CO2 and give it value and store it in a much easier way than a gas, then it's going to go a long way to helping reduce our carbon emissions.
Great. What are your thoughts on oxo-biodegradable plastics? Does it produce benign products from synthetic petroleum plastics, even with their chemical additives?
What was that?
Oxo-biodegradable, all one word.
Okay, I'm not 100% sure what you mean by that. We often refer to these kinds of polymers as oxygenated polymers. I'm not sure if that's what you're referring to. And yeah, so like I was saying, we currently don't understand the effects of degradation in nature very well. It's really hard to study in a lab. It's hard. You can't really go outside, dig up a bit of soil, stick these polymers in, watch them very easily and very carefully. So it's something that we need to think more carefully about how we research that and how we go about studying degradation. But yeah, at the moment, we think that the products they degrade into, so like I said, these ones particularly degrade into diols, hydroxy acids, and carbon dioxide, that they are environmentally benign. Obviously, releasing CO2 into the atmosphere is not ideal, but there are ways around dealing with that, and the diols and hydroxy acids we don't believe are particularly harmful, but we need to study this much, much more.
A question which might benefit from a definition, if you could give us one as well. Yeah. What's your opinion on microplastic rain, and how would we combat this? And I suppose for the lay people amongst us, what is microplastic rain?
I've never heard that term before.
Okay.
So microplastics obviously can enter the waterways, the oceans and the rivers and the lakes. It's not going, as water evaporates, microplastics aren't going to be pulled up into the atmosphere, but that doesn't mean there aren't ways that microplastics can get into the upper atmosphere. If there are freak weather events like typhoons, tornadoes, hurricanes, that can pull a lot of things into the air, which I assume then can rain down. But the possibility of particulate plastic evaporating and raining down on us is very slim. And to be honest, even if it were to, microplastics are almost so well distributed in the environment now. I'm not sure how much more damage it would cause. But if they were to fall on land, they'd likely just get washed back into the sea over time and find their way back. So yeah, I'll have to Google this afterwards in case this is a phenomenon that I just haven't heard of.
Well, there's another question. I'll just go with one more that kind of presupposes a definition here. So if you're aware of this term, let us know.
Let's see.
What are your thoughts on eco-corona in relation to microplastics? Is eco-corona a term that makes sense to you?
Is this? It'd be great if you this in person because I could ask questions back. I think this is talking about enzymes that can eat plastic, essentially. I assume that's what they're referring to. I could be completely wrong. I'm sorry if I am. But yeah, this is a really interesting area of research at the moment where we found certain enzymes that are able to essentially eat types of plastic. They're able to the carbon bonds typically are able to enter a active site of the enzyme, and they can be cleaved and the polymer can be broken up, which is incredibly exciting. Potentially could be an area that would allow us to break down microplastics or even larger pieces of plastics from materials that are typically not biodegradable. My biology knowledge is pretty poor, I have to admit. I didn't study it beyond GCSE, so anything about enzymes and proteins always goes over my head a little bit, but it's something that I've been reading about and we've been talking about in our group quite a bit recently.
To come away from somewhat specific scientific terms and sort of coming back to a big picture, if you like, how do you see the balance between reducing the use of and recycling of plastic? Is it important to also reduce use because of other plastic impacts like carbon footprint?
Yeah, this is a great question. And to be honest, I don't think the answer is particularly clear. Yes, we would like to reduce, sorry, take bits of water. We'd like to reduce how much plastic we're using. But it's not that simple. Yes, we can cut back like straws and carrier bags, and they do have a cumulative positive effect. But like I was saying, it's to be honest, it's a drop in the ocean. And I think if real change is going to come from in this industry, it's going to come from governments, because as consumers we can choose other products, but if, like I was saying, if producing new plastics is going to be cheaper than producing or recycling plastic, then it's going to be very hard for companies to justify making that switch economically. Obviously, there's much more important in the world than just money, but we need governments to incentivize producing more sustainable plastics, encouraging companies to reduce packaging. Yes, it's a combination of everything. Like, I know it's a bit of a cop-out answer, but we need to do everything better and more to solve this.
But governments can influence behaviour as well. A question coming from me, or perhaps an observation coming from me. You know, you go back. I don't know how many years ago it is. You might remember better than me. But when restrictions were placed on the use of plastic bags in supermarkets, the fact that there's a nominal charge made for them, and that just completely nudged people, didn't it? Oh yeah, but things like that are brilliant and incredibly effective. I always carry a few tote bags around with me now, and if I ever get caught out and I have to pay for a carry bag, I'm so annoyed at myself for being in that position. But yeah, governments have a big role to play, and I think every government in the world can be doing more to address this. The industry has a lot of influence, and they're not easy to budge, but hopefully we start to realise the problems that we're causing more and more, and that action is urgently needed, and that prompts governments to take more action. Can I ask another question as well? You're obviously engaged at the real cliff face here. You're getting stuck into research which could potentially have massive global impacts, and to a layperson like myself, something like the David Attenborough program comes along a couple of years ago, which just raised huge awareness of the effects of plastic. Is it about sort of changing hearts and minds as well? I mean, and how do we do that? That's a ridiculously broad question I've just asked you. No. Well, any thoughts on that? Yeah. Well, so Blue Planet 2 particularly was huge. It had such an impact on people. I think most people just didn't realise the impact that plastic pollution had. I don't think I realised to the extent, even though I knew it was a problem. This picture on screen at the moment is from Blue Planet 2.
And yeah, I think that was a big moment. It definitely was with me, and it came out before I decided what area of research I was going to, and definitely played a factor in what I wanted to do. Because there's lots of cool chemistry out there, but for me, I wanted to do something where I could know that it could have a real world impact, and that meant a lot to me. And you know, it definitely stuck in my mind and big factor in a lot of the decisions I've made.
And then lastly, I'm sorry I haven't asked more than one question in any of these sessions, but I'm just really inspired by what you're saying. Does the fact that plastics are generated from petroleum, I mean, I know you mentioned, alternatives, but do the fact that plastics are generated from petroleum, even though petroleum is clearly associated with significant environmental damage, does that give us some hope in that even if we didn't want to do something about this problem, ultimately with petroleum eventually running out?
Yeah, I mean, I think there's a strong argument that we'll, at least for the quite distant future, be somewhat reliant on petroleum-derived polymers. I think there are some applications, particularly in medicine, that it would be very hard to find a good alternative for, and that maybe in time researchers can find something. But what we need to focus on, I guess, is the kinds of plastics we can replace and prioritize. Like, I think a big problem is that we think plastics a synonym for cheap, and we consider these materials to be, they should be cheap, but they really shouldn't be. They are really incredible materials with lots of remarkable properties, and we didn't have these materials until 100 years ago. And I think people need to just understand the value of polymers a bit more and know that maybe we should be paying a bit more for these materials if they're bio-derived and biodegradable. And we should, I don't think we'll ever move away from, at least in my lifetime, move away from petroleum-derived ones completely, but they have their place. But we need to work out how do we make that place as small as possible.
Kam, you've communicated your research interests in this whole area with such enthusiasm and passion, and it's been absolutely inspiring, certainly for me, but I hope also, I'm sure, for students attending. We don't have any other further questions, but to recap, we will send a link to the recording that's generated and the PDF of the presentation, which in Kam's case has got some fantastic enrichment recommendations as well, neatly combining both halves of the delivery tonight. And yeah, I'd just like to say thank you so much. We've had some wonderful talks in this series. It's you've just finished the series on a high. We'll be coming back with more in the next academic year, but I can't thank you enough. And students, thank you for some great questions as well. Kam, over to you.
Thank you. Yeah, I've got some Googling to do now. I need to look up microplastic rain, and yeah, I still have so much to learn. Yeah, but thank you guys.
Okay, thanks very much. We'll end the call here. Cheerio. Good night.
Thanks, everyone. Thanks for joining us. Have a lovely evening. Nice one, Kam. Feel free to head off.